3D printing.
Chris, maybe talk about what, because we don't have a mic today.
Okay,
Yeah.
so like this?
Like that.
Yeah.
Is that,
Yep.
okay. During the dry run, my throat hurt for about 45 minutes afterwards. I really got it tonight.
Nah.
Okay, yeah, I'm Chris Want. I'm going to talk to you about Python and Blender, designing for 3D printing. First of all, I'll talk a little bit about Blender, and I'll talk about modeling meshes. Meshes are what you need to eventually construct before you can 3D print. I'll talk about Python scripting in Blender. I'll talk about exporting for 3D printing, some common issues when you're designing for 3D printing, and I'll talk about the service bureau that I use for my 3D printing jobs. It's called Shapeways. And I don't represent the company, I'm just a happy user. So first, a little bit about me. I'm a longtime math geek. I used to have a job title which was Scientific Visualization Programmer Analyst at the University of Alberta for about 10 years, or maybe a little longer. And during that time, I actually maintained a 3D printer. We had a Z Corp, or as the manufacturers like to call it, a Z Corp 3D printer. And it produces plaster-based models. They're great. It's the one technology that gets you full-color models, but they tend to be a little bit wimpy. Like you can't drop them and stuff like that. I used to be a Blender developer. I'm semi-retired now. When you get a girlfriend, get married, and have a kid, that's what happens. You don't do open source anymore. And I currently work for Westgrid, which is a high-performance computing consortium. So we manage supercomputers at universities in Western Canada. And I don't know how this got me here. Oh yeah, this is a project I did a while ago. It's producing chocolate monkey heads using 3D printing, and just to get a flavor of some things you can do. Looks like, yeah. Yeah. Oh, sure. Great. So yeah, you can go into Blender, design some monkey heads, and have them 3D printed. And then get out your childhood Lego and arrange your monkey heads in a box. Pour in some food grade or food safe silicone. And then pop out the monkeys. And eventually pour some chocolate in. And at the end, you get chocolate monkey heads, which is what everyone wants. So, has everyone here used Blender? Has everyone here used Blender, thought it was nuts, quit using it, reinstalled it? Yeah, that was my experience. Sadly, that was like 15 years ago, so I've been using it a long time. So a little bit about Blender. It's a free open source 3D animation suite. It supports the entirety of the 3D pipeline: modeling, rigging, animation, simulation, rendering, compositing, motion tracking, and video editing and game creation. It's released under the GNU public license. It has a pretty complete Python API, so you can do lots of stuff with it. My recommendation, if you're going to use Blender, is use a keyboard that has a numpad, which a lot of laptops don't have. Use a 3-button mouse with a scroll wheel, and get the best graphics card you can afford. That last one is maybe not as important as it used to be, because all graphic cards are fast now, so any gamer card is just fine. In Blender, there's 3 ways to access Python. There's probably a fourth way, but I'm only going to list three. One is through a built-in text editor. Another one is through something called the Python console. And the third way is to write installed scripts, put them in your file system somewhere, and Blender will know where to find them and load them up at start time. And then you can have little tools appearing in your menus and stuff. So for the sake of this tutorial, I'll run scripts through the text editor. And the way it works is that when your mouse is hovering over the text editor, you press an Alt-P and your script runs. So this is what the text editor looks like, this big gray thing here. This is a console here, so you can enter little commands that will interact with your 3D scene. And I won't show you anything about the about installing scripts into the menus. In Blender, everything is done as an operator when you're modeling, and these are little bits of code that actually do something, as if you're actually running them through the menu or doing a hotkey. And the Python API maps really well to these things. What you'll see is, if you're going through the menus and you hover over an item, you'll see a tooltip. So in this case, I'm hovering over select inverse. And right under what it says what it is, it gives you a little Python API description of what little bit of code you can execute to perform this operation in a script. So it's quite handy. Oops, almost wrong button. So the name of the module that you're going to use when you're in Blender is called BPy or BPY, and it has various parts. One of those parts is bpy.types, those are your your classes in the API. So you do like bpy.types.mesh.new, that sort of thing. If you want to query the state of your scene graph and the memory in your program, all the objects you have there, you do that through a bpy.data module. Operators, which I discussed just a moment ago, they're through this bpy.ops. And there's also something called bpy.context, which gives you a little bit of information about information about the state of the program. Like, for example, what the current view that you're in or scene. You can get handles to these if you're doing something that's dependent on this kind of data. Any questions so far? Okay. Am I still maintaining an adequate volume? Up more?
No, you're good.
Okay. Yeah, when you go like this, it's hard to tell. Thanks. Oops, wrong button again. So objects and their data. An object is sort of a catch-all class for just about everything in your scene. The object is the type of object is defined by this attribute called data. So a little example there. I'm running that in the console in theory. So you can grab a object called profile and stuff it into something called ob. And then when you look at ob.data, it says, hey, that's a mesh, because it points to bpy.data.meshes. And it turns out that in this case, my mesh is named plane. When I model, most things start as plane, and then they turn into something else. Second object is like a camera. So you can grab an object called camera, then query its data, and sure enough, it points to a bunch of to something in the sort of database of cameras called camera. So so that's sort of the unique data based on the type of object you have. So if I go back here, here's my object called profile. This one's called thingy. It's also a mesh. These two. Here's a camera over here, and here's a lamp. And if I go into the little console here, I'll do some live typing because that never goes wrong. Data objects. Usually if you're doing a lot of rendering, you add a lot of lamps, so. That's how you access your data through the console. Now I could do things like change the position of that object through the console, but I don't want to risk messing it up. So meshes in Blender, they're composed of 3 different types of primitives. One is vertices, which are little dots in 3D spaces, they're locations. Another are edges, which connect any 2 vertices. And a third type are faces. They're typically triangles or quadrilaterals, which connect 3 or 4 vertices. For 3D printing, we don't really care about edges. They just don't print very well, so because they're one-dimensional manifolds. The things that we are interested in are vertices and faces, because faces, well, you'll construct a whole bunch of triangles to create a coherent mesh, which will enclose a volume, and then you can 3D print that. So this is, I'll talk a little bit about how to construct a mesh in Python. So the way you think about it is you say, okay, I have some vertices. They're going to be listed as XYZ, 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 denoting all these positions in space. Since we all love the C programming language, this will be a 0-based list. And what we'll do is once we have our vertices, we'll start constructing faces and edges as pointers into those lists of vertices. So if I want to connect vertex 0 and vertex 12, well, I put into a list 0 and 12. I'll show you that in a moment. So here's an example. Here's a list of vertices. It's a Python list and of tuples or other lists, a list of lists. I have 4 of them. There's vertex 0, vertex 1, vertex 2, and vertex 3. When I want to think about edges, I can create a list of edges. So if I want to connect vertex 0 and vertex 1, and vertex 1 and vertex 2, I would list them in this list, which is also a list of lists. If I want a face, or many faces, I would list them also as defining what the endpoints of each of these faces is. So here I've connected vertex 0, vertex 2, and vertex 3. So now we get into the Python API. There's a function called bpy.types.mesh.fromPyData. So I have my verts, edges, and faces lists like I've just defined in the slides before. I create a new mesh, and then from this new mesh, I give it the name me. I don't mean me as in me, but I mean short for mesh. And so I do me.fromPyData, and I supply those 3 lists. And then that's great. I have a mesh, but it doesn't exist anywhere other than in memory. So I have to attach it to an object next. So I create a variable called ob, which creates a object in my scene, also named ob. And I say, hey, remember that ob.data stuff? Well, we're going to assign this me mesh to that. So we still don't have anything in our scene yet. We just have the connections ready to go. So eventually I have to get a sort of a pointer to our current scene, and I link our object to the current scene, and that will actually put it in the user interface when you're using the program. And I added a couple of bonus lines there. They're not needed for the sake of this example, but from there you can make this your active object and select it and do other stuff. So that's how we get our first Python mesh object. Any questions? Great. I'm going to go through a little bit of an example of how to produce a thingy. This thingy is kind of like a surface of revolution, if you know what that is. So you start with a profile shape, which is a 2D curve. In our case, we want it to be a closed curve, so it's the beginning and the end match up. And then we sort of extruded along a path, and from there we were able to produce a solid that we can, in theory, 3D print. So this isn't a surface of revolution because we take a more, if you know what that is, because we take a more complex route than just going in a circle. So to specify my thingy, I first need a profile shape. I'm going to specify a radius. I'm going to specify a resolution. So if I go over here, here's one I made earlier. So the resolution are all these sort of ribs that you see here. Here's my profile shape. What I'm going to do is I'm going to do a sine wave as I go around. So you'll see there's 4 peaks, 1, 2, 3, 4. So that means that I do 4 cycles of the sine wave. And those peaks all have an amplitude, which I can specify in the script. So if I go to the script, I can say, okay, maybe I want to have a radius of 10. And then I can instantly, whoops, what happened there?
You used to leave his number of cycles.
Oh dear. Okay. Okay, so if I want to, thank you, have a radius of 10, and it still doesn't work. Oh, there it does. So now I've doubled the radius. I can increase the amplitude. And I'm going to make sure I use my correct Alt key, or otherwise it doesn't work. I can increase the number of cycles to 16. And looks like Charlie Brown's t-shirt. So in order to have more cycles, you got to bump up the resolution. And seriously, I have something that's a bit more smooth. Bring down the amplitude a little bit so it looks nicer. So yeah, and then there's the profile shape, which is here. And this I don't want to script, I just want to model it. So I come along and I grab some points and I drag them, do some stuff. And then when I'm done, I can just run my script again and the shape updates. So now the reason why I'm doing this is that I've actually done this and had things 3D printed. Not this particular shape, but I designed some rings. And part of the reason why I did that is not because I actually wanted any rings, but because I wanted to try out some of the Shapeways metal materials. So I'm going to pass these around, and in a few slides we'll talk about them. I know Gazim's already seen them. So. Okay. So the sort of strategy we'll take with a script that'll produce the thingy is first we'll sort of grab our source mesh, which is depicted there in the middle, and we'll make a whole bunch of duplicates. So our resolution variable will determine how many duplicates we do. And then when we're done, everywhere in our original profile mesh, which is viewed there on the left, everywhere you have an edge in the new shape that we're producing, we'll construct a face that connects any sort of adjacent sets of vertices. And since we're supplying basically pointers or indices into our list of vertices, we'll just exploit the fact that we're connecting vertices whose indices are the number of vertices apart from each other. I'm not going to get into big details, but I'm not going to go into deep detail, but I just thought I'd just mention that. So where do you start? Well, the first thing you do is you import BPY. When you're writing a script in Python, you always have to import BPY if you want to use any of the Blender API stuff. With a console in Python, you don't have to do that. It's already implicitly imported. But with a script in the text editor, you have to do BPY. And then I'll import some trig functions, and then I'll set up my global variables. I'll just mention that this isn't the best code I ever wrote. So to be a good example of how this stuff all works, not to be good code. So I'm going to use some global variables and stuff. So I'm going to create a function called main, because that's how I like to do things. First I'll get a handle to my old object called profile, and then I'll grab a handle to its data, which is a mesh. So I'll call it old me or old mesh. Then I'll just query the mesh a little bit to get the number of vertices. I don't actually need the number of edges, so you don't actually need that line, but I even wonder if I need the number of faces. Actually, it doesn't have any faces, so no, I don't. Actually, okay, I do need the number of edges, but I don't need the number of faces, because it doesn't have any. And then I'll initialize a couple of lists. One is called verts, to hold our new vertices, and the other one is called faces, which will hold our new faces that we'll construct. So I continue with my main function. I loop over the number of our desired resolution, and then through every vertex in the old mesh, I'll make a copy, and then I'll transform the position, and then I'll append it to our verts list. Once I've done that, I can start constructing my faces. So this time I'll loop over the edges in the profile mesh, and I have a test there which queries whether it's a loose edge or not. Technically, faces are surrounded by edges, and if we had faces in this mesh, which we don't, this would be important that we just want the sort of stick ones, not the ones that are attached to faces. Hope that's not too confusing, but from there, we have a little function that transforms edges to faces, and we append it to our face list. And then we finally create our new mesh, call it thingy, and we run our from PyData function as we did earlier. So I'll pass it our verts list. We have no edges that we really want to add that aren't connected to faces, so we give it an empty list for the edges, and then we pass it a faces list, and so that produces the mesh, and then we create a new object, we get a handle to an existing object called thingy, and whatever mesh it had, we discard it, and we just attach this new mesh to the data that's pointed to, that object points to. So I'm not going to go over this, but this is a bit of trig for the sake of completeness for transforming the position of where the new vertices go. You'll see our global variable amplitude is there. We're doing some signs. The number of cycles is in there somewhere, and then we just return the new location. Here's the function that converts edges from the original mesh to faces in the new mesh. And finally, we run main, and the program runs, and we get the beautiful thingy object. So, yeah. Okay, so sometimes you want to print something, but it just can't exist in 3D space because it doesn't enclose a volume. Here's an example where I basically have a thingy object, and it's missing a chunk. So what you have are these bare exposed edges. This is called a non-manifold surface. As far as 3D computer graphics go, the definition of what is a manifold surface is that every edge in the mesh has two faces attached to it. So if you do that, if you're able to do that, you'll always get a shape that is sort of has these nice differential geometry properties, and as long as your faces aren't too degenerate after that, you should be able to 3D print it. So you need an interior that has to be clearly defined. Any questions about that?
Is there a fill function? Like, can you tell it to fill in?
You can, kind of. I mean, you may not get what you want. So if I bump down my number of, or my resolution down to 8 on that, so now we have something that's pretty simple looking. I'll grab one of these ribs and delete it. So now we have our non-manifold surface. And if I grab the right thing, there we go. And it has something called beauty fill or something like that. And it just, I've now blocked off this sort of perversity that prevents us from 3D printing. And now I have to do it over here too though. And so now we have a solid again. And in theory we can 3D print that. Okay, you can thank my wife for this slide. This is a visualization of simulation of the inner and outer magnetic field of Neptune. I was quite proud of it. It has a beautiful little cage around it and all these magnetic field lines. And there's a few places where the magnetic field lines didn't quite make it. They got knocked. Now this is printed with a plaster-based 3D printer, in particular the one at the U of A that used to be there. It's been shut down now. You can order this kind of material from Shapeways though. If you want a full color model that's a little bit wimpy. You're also going to have to worry a little bit about faceting. So this is something that, I hope you can see that slide. There's one of those meshes has a lot more detail than the other. I've added the little comment there that the subdivision surface modifier is your friend. And so if we go back to our original thing, maybe I'll bump up the resolution to 16. Rerun it. We have something that looks pretty darn blocky. If you're hoping to get a smooth organic shape, that's not it. So you can go over here to this little wrench, add a modifier, and subdivision surface. And I don't know if you can see, but we've just doubled sort of the resolution without increasing the complexity of the mesh, at least the cage mesh. So if I go into what's called edit mode, we still have our same mesh again, but we get double the resolution. And if I bump up the subdivisions again, you get something that's really quite smooth. The reason why we want to keep the cage mesh or these control vertices low is because then you can modify the smoothness without having to move each individual vertices. The fewer vertices you have to move around, the happier your experience when you model will be, because it'll be just gets too complicated after a while. So if you explore with Blender, which I'm sure you all will after this talk, look up that modifier. So eventually we'll want to export to get it to the 3D Printing Service Bureau. So the file menu, export, there's a menu called export. There's a few formats that I guess would be good to use. One is STL. STL is short for stereolithography, and you can produce those if you want monochrome models. So I'm going to toot my own horn a little bit. I was the first person to add STL format to Blender. It was written in C, and it's since been long ago replaced and rewritten in Python. But that was because I was maintaining the 3D printer at the U of A, and I needed an export format that we could use to get models out. There's another format called X3D. This is like the XML successor to VRML. Now I'm going to recommend it for color, but having never used it, because all of the models that I've ever produced were in VRML, which was in an older version of Blender, and VRML is no longer supported as an export option, at least not out of the box. And so X3D, I would guess, would be the logical successor, and Shapeways has support for X3D. So think about the size of your object before exporting. Blender doesn't really have units, but I can query my dimensions here. In fact, I can do some strange things and modify the X, Y, and Z scaling of this object. So if you know you want inches and you know you want it to be 21.479 inches, you're good to go. But if you wanted it to be 10 inches, you should probably rescale it and then export it and then upload it to Shapeways. So Shapeways is what I use. Again, I don't get paid to mention the Service Bureau. They have a really great material selection. We've passed around some metal coins. I actually have some more models here. They were done, most of them were done at the University of Alberta. So I'm not going to pass these around because, well, as we learned from that dreaded slide with the magnetic field of Neptune, yeah, they don't last very well. So this is actually the Earth's magnetic field, the solar wind sort of simulation. But you're welcome to come up and check it out. And I used to do little gimmicky coins that we used to hand out for the 3D printer. These are full colored also. And there was a vendor that wanted to send me wanted me to buy a 3D printer. In particular, the company's name is Objet. They make awesome 3D printers if you want plastic. So this is a little whistle. I had them make me as a demo. I used to produce this on the U of A 3D printer out of plastic, but I can't find any of them. I had a bunch of them. Doesn't really whistle as good as I'd hoped. The plaster one works pretty good. It has a little propeller that spins around. And my coworker John's here, and we designed some channels inside there that actually direct the wind flow towards the propeller blades to get it to spin right. And it's got little flames on it. And, well, anyways, I guess I had too much time on my hands at the U of A sometimes. So, yeah, so the material selection is good, and the price is pretty good, turnaround's pretty good, and I'll show a couple examples of what you can expect, or at least what my experience was. And one cool thing is that you can set up your own little shop, and I thought, hey, I'll give that a go, and so I produced my own little Shapeways shop, where I have the rings that we're passing around, and some dies so that you can make your own chocolate monkey heads at home. So far I've had 0 sales. But the point was I just wanted to see what the experience was to create the shop. And who knows, maybe someone one day will buy something.
So, sorry Chris.
Yeah.
If somebody were to go and want to buy a ring, how would they choose a size?
First of all, their finger would have to be size 7. Okay. There's weight loss programs you can do if you need a better one. No, I mentioned on the site there that if you have a different size, you can contact me and I can try and fit what they need.
When you use Blender, can you calculate the model material you're going to need ahead of time?
You can. There's a 3D printing toolbox that you can have as an add-on, and it does volume calculations. And Shapeways has the price per volume listed on their website. I would just upload it and then figure it out there, because they have like 20 different materials, or even more. So I just export the object, upload it, and they'll tell you exactly how much you're going to pay before you press print. So.
And I guess you have to be conscious of how the printing process actually works. You're not going to do like an inverted pyramid, right? So it's going to follow.
Yeah, some materials, some objects will require support materials. So the plaster-based ones, you basically lay down a layer of plaster you print on top, then you lay down another layer of plaster, all in just sort of like a sheet of paper. Just chuck it down, print some binder fluid on that, do another layer, layer. So eventually you have this brick of dry plaster that's supporting your upside down pyramid. So it's actually being suspended in this cube of plaster. Most of it's dry, this part isn't. So then you do this sort of archaeological dig to dig out your precious artifact. And so that's how the supports works with this technology. With the metal ones actually, I believe they work the same way. So you're dealing with metal powders now. And instead of print heads moistening plaster, you have a laser or something that fuses the, pretty sure it's a laser, it fuses the metals but it does it layer and layer, you know, each one layer at a time, bottom to top, and then you have this brick of mostly dry or unfused material that you can remove and take your hard object out. This is the plastic one by Object. They actually they print in plastic, and then they spew out this plastic, and then their print head has a little UV light that cures it, kind of like when you get a filling or something. But they print two materials at a time. One which is what you see here. The other one is a water-soluble support material. And they do basically the same thing. They go print back and forth. Each time it's printing like a whole page of material, but it'll be the two different types of materials. And then they put, when they take the block out, they'll put it into like a water bath with an agitator, and that'll remove all the support material away, and you're left with your object. So, to make what should have been a short story long, you don't have to worry about it. Like if you have a MakerBot, you might have to worry about it, but if you're printing to a service bureau, don't worry about support materials or anything like that. Okay, here's an example. I didn't bring it. My wife has this Pandora charm bracelet, and I thought, what the heck, I'll make her one charm with her name on it and another one with our daughter's name on it. And the Shapeways, they do lost wax casting. What that means is that they 3D print your object in wax, and then they put like casting sand around it. Then they melt out the wax, and then they fill that void with silver. And then at the end, they break out your object from the sand, and you wind up with these two things, which they looked okay. I chose the most expensive material they sell. It's called polished silver. So if I did just plain silver, unpolished, it would have been a lot cheaper, but since polishing has some kind of labor component to it, it was a bit expensive. I paid $111 for both objects. They're both smaller than a dime, but thicker than a dime. I ended up incurring a brokerage fee of $16, and it took 23 days from when I clicked print to when I had the object in my mailbox. That's pretty good. So the rings, there's 4 different materials. There's stainless steel, gold-plated steel, raw brass, and raw bronze. I paid $76.60 for all 4. So that works to about $18 or something per object. There was a promotion. If I spent more than $75, I got free shipping. So that's why I chose $76.60. And it took 15 days from print to the time that I had the 4 rings in my hand. There's a little Easter egg on this slide. On my fridge, I have this fridge magnet that has Python keywords on it. I never did break it apart and do the individual keywords and lay them out on the fridge, because my baby would eat them. But my 2-year-old daughter. But anyways, that's those are my 2 experiences with Shapeways.
Excuse me, were those rings hand polished as well, or is that?
I think the ones, let's see. The ones that say raw had no post-processing on them. The ones that don't say raw, I think there was some kind of polishing going on. What I'd suggest, if you are interested, check out the website. They'll tell you what the sort of process is. I have mixed feelings about polishing, because with the silver one, I felt some of the detail got eroded away. I have a feeling they'd also look kind of crappy if I didn't have them polished. So what I might do next time is get them to not polish them and do selective polishing myself. It's a learning experience to try all of them, so I'm hoping that if you guys take a look at the rings, it might give you some ideas of what you can expect. So here's a bonus 3D visualization that was produced in Blender. This is from a site called Laser Crystal Awards. And it's another, I don't know, I really get off on magnetic fields. I studied dynamical systems in university, and they're trajectories through a vector space, and I like them. So here's what it looks like in real life. And what's going on there is that this company, which does awards basically, you can send them an STL file and they'll etch it inside a piece of plastic for you. So this was a 2-inch block. It's $20 to have it etched. The light base, which you don't need, is $20. It does look kind of cool on the base though. And shipping was $20. But if you ordered 5 of these, the shipping cost was still $20. So if you're ever going to do this, maybe design 5 different things and send them all at once, and exploit that sort of, get more bang out of your shipping buck that way. So yeah, that's another technology you can look at. And here's another one where I'm sure you can all see it from over there. Actually, it'd be kind of interesting to see if it's, nope, did not work. Okay. So this is like a test object. I have the word test a bunch of times. I have a bunch of U of A logos, a bunch of monkey heads, and a bunch of squares that are embedded inside each other, just to see. I actually sent this as raw points rather than as an STL surface, because it was for a project. I was working on a project where I had to show an inner shell and an outer shell. The scientist was studying material. Well, he's a professor in material engineering, and he was studying the solidification of metals. And so what he'd do is get little bits of aluminum liquid and then let it solidify, and then he'd send it to a CT scanner and then check out the cavities inside. So in order to look at the cavities, he wanted a visualization. He wanted to use 3D printing, but looking at cavities in anything with an opaque surface isn't a good idea. You just can't see through it. So this seemed like a good technology to use. And again, to make it should have been a short story long, I ended up sending raw points just so that I can manipulate the density of these surfaces, so I can have a more wispy surface on the outside and then a more solid surface on the inside of what I was printing. You can check it out with some of these cubes in here. You can get different details, levels of detail, depending on what density of points you render. So, yeah, I ended up doing the retirement gifts at our department for a few years, because I had this skill where I could produce etched cubes with people's names in them. So if you want more information, check out the Blender website. Here's a link to the current Blender Python API. It's horrible, but at least it's something. There's a link to the 3D printing add-on if you choose to sort of add it to Blender. There's a wiki page on using the Python console. And some guy in the Netherlands wrote a DVD or produced a DVD on 3D printing, how to learn all about it using Blender. Okay, thank you. Any questions? You feel free to look at any of this stuff during the break. But, yeah, any questions?
I just think if you could make one of these models available online as part of the slides, something we could play with and then import it into
Yeah.
Shapeways or whatever, that'd be really interesting.
Well, the thingy, I have the Blender file there, so you can certainly download that file and change the script, change the profile, rewrite the program so that it's actually good code. Yeah, do all sorts of things. Yeah. Yes, sir.
It's like a blender, the logical choice for 3D printing, or would you use like a CAD program?
Yeah, CAD would be better in many ways. Things like SolidWorks, where it's like, well, it's called SolidWorks for a reason. The goal is to produce solids. The goal of Blender is to model meshes. Meshes have problems sometimes unless you're very careful about how you model them. Some people want to punch Blender when they use it, or at least their computer screen, because it's difficult to learn. So I would say the price is right. There's that. I like it because I've been using it for 15 years, so I can make anything I want. If you're used to AutoCAD, by all means use that. It also has STL export for 3D printing. So it's not the worst choice you can make, but there's, yeah, your engineering and CAD packages might be better choices.
So you did your own rotate and translate. Did nothing Blender provided come with translation and rotation?
You mean in my little transform
Yeah.
function? Yeah, it does have that sort of thing.
So you go ob.translate, ob.rotate or something.
Yep. I actually was working on a second example where I basically used modeling operations to construct the same thing. And I ran into a snag. I wanted to use a pivot point for the rotation, which in the modeling interface is easy to do. So if I'm here, what I might want to do is grab my profile object, go into edit mode, select everything, move it over here. But you see this little thing that looks like a donut with a crosshair? That's called a 3D cursor. And so if I want to rotate, I want to use that as a pivot point, right? So I can extrude, rotate it around a bit, extrude, rotate, and I can make my thingy without doing a script. But I can also write these operations as a script. But for some reason, I just couldn't find how to get the position of the 3D cursor. And part of the problem was because this context variable, it depends on which viewport you're in, but I wasn't in a viewport. I'm in this text editor, and for some reason it just wasn't working out, and I thought, screw it, I'll drop this slide. So.
And a question about STL. Is STL like voxels, or is it actually faces, or?
It's a horrible format. It's triangle, triangle, triangle. So XYZ1, XYZ2, XYZ3. That's a triangle. XYZ1, XYZ2, XYZ3. That's another triangle. And it just does that over and over again. Now, at least even with our little example here, we're defining our faces based on a list of vertices so we can reuse some of them. The STL format doesn't have that. So not only is it not voxels, it's just crappy.
Probably compresses well with something like gzip or something, no?
Could do. Yeah.
If you've got repeated vertices.
Yeah, I mean, first of all, if you're worried about file size, it has two subformats. One's ASCII, one's binary. The binary one isn't too bad. The ASCII one gives horribly large files. But yeah, you can exploit compression. But still, you're probably not going to get as good compression as if you define all your vertices and then define a list of faces, just because you can reuse that stuff. And I mean, maybe it'll only be 10 or 20% difference, but yeah, who cares? 2014, we have 4 terabyte hard drives, so it's the file size probably isn't too much of a concern. It's just a bad format.
Is the STL built into Blender now, you said? Or did you say it's?
Yeah,
like-
that's right, it's
Oh.
been there for a long time, just under the file menu, file, export, and here's STL here. And I think that just writes out a binary format, not the ASCII, and you can import your STL files too if you want, and, yeah. Any other questions?
Wait, so when you import your STLs, like, you said that it's all like triangles.
Yeah.
Is your model gonna look, is it gonna be just that, all bunch of triangles?
Yep.
Okay.
Yeah, it's gonna be triangulated, so it'll look,
So working with it afterwards is gonna be pretty difficult.
yeah, it's gonna look like this, and I just converted my whole mesh into triangles rather than,
Oh, okay, so.
now Blender has a little function that, see, is that it? Yep. It tries to find coplanar stuff. It didn't do a good job with these guys, but it actually collapsed most of those into quadrilateral faces.
There's some hope.
So there's a bit of hope there, yeah. Any other questions? Okay, thank you for your attention, and feel free to look at the
Good, thanks, Chris. So we have pizza now. We're gonna leave the models out here. Please don't spill pop or pizza. I'm not sure, how well they would take that.